Welcome to the 20th lecture of my series on classical thermodynamics. It has been quite a while since my last lecture, so I thought this is a good time when we can recapitulate whatever we have done so far very quickly and then go on to look at some applications. First, let's talk about thermodynamic potentials. We have seen that complete thermodynamic information of a system can be obtained if you express the internal energy of the system in terms of its entropy, volume, and number of moles. Of course, this is only for very simple systems which can be described by a single component and only as hydrostatic work as a means of doing work available to it. More complicated systems would have a similar expression for U, but with more extensive variables sitting in the place of the arguments. For example, if it were a two-component system, you would have N1 and N2 for the two components making up the system. We will talk about more complex systems later, but for the time being, let's stick to simple systems which can be described by a single component. And a function like this, U expressed as a function of the entropy, volume and number or amount of particles making it up, gives you complete thermodynamic information about the system. Whatever thermodynamics can tell you about the system can be obtained from this function. Of course, as we had already said earlier, this function itself cannot be obtained from thermodynamics. It can either be obtained experimentally or via some more fundamental theory like statistical mechanics, something we are going to talk about hopefully later on. Now we have also seen that you can change the variables involved here. Note that the independent variables in U for this expression are all extensive variables. Of course, the derivatives of U with respect to any one of these variables, temperature, for example, when you differentiate with respect to S holding V and N fixed, pressure, or rather the negative of it, when you differentiate with respect to V, and so on, are all intensive variables. Now, if you want to switch an extensive variable out in favor of its intensive counterpart, it can be done following what is called the Lagrange transformation. In this, you subtract from the function the product of the variable that you want to get rid of and the function's derivative with respect to that variable. So you can switch out V from U by subtracting from U the product of V and U's derivative with respect to V, which is minus P. And this leads us to enthalpy, H, which is U plus P times V, and it's a function of S, P and N. When we say H is a function of S, P and N, what we really mean is that if you were to express H as a function of S, P and N, you would get complete thermodynamic information about the system, just as U as a function of S, V, N and N had complete information. Similarly, you can get rid of the S and bring in T by subtracting from U the product Ts, and this gives rise to the Helmholtz free energy. And finally, if you were to subtract Ts from the enthalpy, that is add PV and subtract Ts from the energy, you end up with the Gibbs free energy, G, a function of T, P and N. Now, as we have said, each one of these thermodynamic potentials has complete thermodynamic information about the system, provided of course that it is expressed as a function of the appropriate variables. U expressed as a function of say T, V and N will not have complete thermodynamic information. It's only when you express the Helmholtz free energy as a function of T, V and N that it does have complete thermodynamic information, and so on for the other thermodynamic potentials. Now, the fact that these functions contain complete thermodynamic information actually follows from the differentials. If you take the differential of u, you end up with Tds minus Pdv plus mu dn, which tells you that if you were to differentiate u with respect to s, keeping v and n fixed, these two terms would drop off and you are going to get temperature as a function of s, v and n. Differentiation with respect to v will give you pressure, or s negative, as a function of s, v and n. If you wanted pressure as a function of temperature, volume and n, you would have to eliminate s between these two expressions. Now, similar to du, dh, df and dg all have rather simple looking differentials. The fact that dh has a plus vdp instead of the minus pdv of du means that if you were to differentiate h with respect to pressure holding entropy and n fixed, you are going to get the volume, and so on. What is actually unrelated, at least not directly related, but very important, is the following. Because u is an extensive function of extensive variables, the Euler theorem about homogeneous functions in mathematics leads to this particular form for u. U is actually equal to Ts minus Pv plus mu n. And adding Pv to that gives you h, which is just Ts plus mu n. Subtracting Ts from u gives you minus Pv plus mu n for f. And taking away Ts and adding Pv to u gives you g is equals mu n. These expressions are going to be pretty useful later on. Now, as we have just said, you can find out the various thermodynamic quantities by differentiating the thermodynamic potentials with respect to their arguments. Here you can see a list of those relations on your screen, and I'm not going to repeat all of them. We have already just said how you can arrive at these. Just start with the differential of a thermodynamic potential, differentiate with respect to one variable after another, and you are going to get these relations. And if you want these thermodynamic quantities as arguments of other variables, all you have to do is eliminate whatever extra variables you have. It is in this manner that once you have u as a function of svn, or h as a function of spn, or and so on, you can get the entire thermodynamics of the system from that. Now that we have seen, for example, that temperature is del u del s at constant v and n, and pressure is minus del u del v at constant s and n, it immediately follows that if you were to differentiate t with respect to v, keeping s and n constant, and minus p with respect to s, keeping v and n constant, what you would get essentially del 2u del s del v on the right hand side, and del 2u del v del s on the left hand side. And as long as the functions are smooth, these two partial derivatives, the mixed partial derivatives, are equal to each other. This allows us to equate these derivatives. Del t del v at constant s and n is equal to minus del p del s at constant v and n. If you did the same thing with the derivatives which come out of h, namely t and v, and differentiate the first one with respect to p holding s and n fixed, and the second one with respect to s holding p and n fixed, you would again get an equality. And you can go on in this manner for each one of the four thermodynamic potentials and end up with four relations between partial derivatives of the arguments with respect to each other. Now, in most textbooks, you will find a version of these expressions where constant n is not mentioned. Indeed, if we go back to our previous set of differentials, the expression for mu usually is not mentioned in most textbooks. But there is a very good reason for that. In most situations, we talk about closed systems, systems where n is fixed. So, how fast do any of these thermodynamic potentials change when you change n, keeping the other two variables intact, is not really something you're worried about. And since n is constant anyway in such systems, You don't write T is del U del S at constant V and N. You just write T is del U del S at constant V. And so on. And similarly, for these four relations between derivatives, the so-called Maxwell relations, usually they are written without mentioning the constant N. Of course, you can find out relationships between derivatives with respect to N and derivatives of mu with respect to other variables by following the same procedure, but they are not really used that often. That often does not mean that they are not used. Sometimes, depending on your application, they might be pretty useful. But in most situations, we deal with closed systems and we don't really mention constant N all the time. Just to illustrate an application of these Maxwell equations, let's start with this expression. du is TdS minus PdV plus mu dN. Now, one might very well be interested in figuring out how fast does U change with volume once temperature and number of moles is held constant. From this differential, it's pretty easy to see that the first expression becomes T del S del V at constant T and N. The second expression, dV with respect to V, is of course 1, so it just gives you minus P. And mu dN vanishes because N is being held constant. Once again, in most textbooks, you will see the same relation without constant N being mentioned because that's taken to be the obvious situation anyway. Now, according to one of the Maxwell relations that we have figured out, del S del V at constant T and N is the same as del P del T at constant V and N. So this is an expression that we get for the rate at which U changes in volume once you hold temperature and number of moles constant. The advantage of this expression over the previous one is that the right hand side of this expression can be completely figured out once you know the mechanical equation of state. How does the pressure of a system depend on its volume, temperature and number of moles? For example, if you look at the ideal gas where PV equals nRT, this derivative del P del T at constant V and N is simply nR over V, and that's the same as P over T. And that tells us that del U del V at constant T and N is 0. This of course was figured out long time ago, long before Maxwell's relations etc. came into being, by Joule as an experimental fact. But Joule's experiments had no thermodynamic basis at its time. This was just an experimental observation. Only when the second law came into the picture and we managed to derive results from it, including the Maxwell relations, were we able to theoretically establish that the internal energy of an ideal gas would not depend on the volume if its temperature and number of moles were intact. Note that the microscopic picture of an ideal gas would make this statement obvious, because in an ideal gas, you have a bunch of molecules which are ideal zero volume particles moving around and they do not interact with each other except by colliding. Now during collisions, the net energy is conserved. That's basically what an elastic collision would do. And there being no potential energy involved here, there being no interaction between the molecules, changing the volume does not change the internal energy at all, as long as the temperature, which is a measure of how fast the molecules are moving, is held fixed. So once again, thermodynamics allows you to understand this even without knowing what is going on inside microscopically. Of course, a microscopic theory may or may not be more satisfying depending on your point of view. Now with this recapitulation out of the way, I'm going to call this a recapitulation too, because I'm pretty sure I've worked this out in one of the previous 19 lectures. What we are going to do is look at a few applications of the second law which we have not covered so far. The first result that we are going to cover is the so-called available work theorem. Now this theorem is often mentioned in textbooks in a slightly sloppy manner without explaining the context fully. So I have seen that plenty of students have misconceptions about what this theorem really says. So I am going to try to be careful about stating exactly what this says and also, quite importantly, what it does not say. Now, the setup for this theorem is the following. A system undergoes a change from an initial state I to a final state F. So this is fixed. You know the initial state of the system, you know the final state of the system. What is the maximum amount of work that can be extracted from the system due to this change? That's the question which the available work theorem tries to answer. Now the answer to this actually depends on the surroundings of the system. This is the part which has to be stressed, because unless you are very sure about what the surroundings are, you cannot give a definitive answer to this question at all. So let us start with something very simple. You have this system in the state I evolving to the state F. In the initial state it had internal energy Uy, entropy Si, of course volume Vi, temperature Ti and so on. In the final you had Uf and Sf as well as Vf, Tf, etc. We are going to focus on U and S because those are the important parts for this theorem. And let's say this system, as this evolution is taking place, is interacting with one reservoir and one reservoir only. So the heat exchange, if any, occurs with only this one reservoir at temperature T. So this is the setup in which, according to which I am going to state the available work theorem. Now, if W is the work done by the system during this process, then Q, the heat that flows into the system, has to be equal to delta U, the internal energy increase, plus the work that the system is doing. I know that previously we had written this as delta U equals Q plus W, but there W meant the work done on the system. So here, let's be careful. The work here is work done by the system. That's the available work that we are going to talk about. So the heat that the system absorbs from the surroundings is delta U plus W. Of course, when you say system absorbs, strictly speaking, absorption only when Q is positive. A negative Q would mean the system actually releases heat to the reservoir. But the important point is, the only absorption or release, whatever is happening with this one thermal reservoir at temperature T. So how much heat is given to the reservoir? The negative of this, minus W minus delta U. Now, this process is almost certainly bound to be irreversible. After all, we did not say that the temperature of the system is T. The temperature would be some temperature Ti to some temperature Tf, neither of which needs to be equal to T. That of course depends on the initial and the final states. And so if you are exchanging heat with a reservoir at a finite temperature difference, that exchange of heat is definitely irreversible. However, as far as the reservoir is concerned, all that matters for its state is how much energy it has. So the only thing that you need to worry about is how much heat was given to it. So, using the basic idea that entropy increase is equal to the heat absorbed by the temperature under reversible conditions, integrated of course if the temperature is a variable, here what we need to do is the net heat absorbed is minus W minus delta U by the reservoir, and the entropy increase of the reservoir is this divided by the temperature of the reservoir. The idea here is that we can always think of a process in which the same amount of heat was given to this reservoir reversibly, and in that process, of course, the change in entropy would be minus W plus delta U by T, and since entropy is a state function, it does not matter how you did it. As long as you went from the initial state of the reservoir with some energy and minus Q amount of additional energy after that, the entropy change is going to be given by this. Now, during the process, there has been an entropy change of the system itself. So, the entropy change of the universe is the sum of the entropy change of the system, delta S, Sf minus Si, added to the entropy change of the reservoir minus W plus delta U by T greater than or equal to 0. Now this can of course be written simply as T delta S greater than or equal to W plus delta U. Remember, T is a positive quantity, so multiplying by that does not change the sign of the inequality, and we can now bring the delta U to the other side and end up with our theorem. The work which the system can do under circumstances when it's in thermal contact with a single reservoir temperature T has to be less than T delta S minus delta U. You cannot get more work out of the system than this. Now, sometimes some books, I've seen some books which do this, they write the right hand side as delta of Ts minus U, which is of course correct because T is constant throughout the process. And then, given that U minus Ts is the Helmholtz free energy, they sometimes write this as minus delta F. And thus one version of the available work theorem, which you can find in some not so good textbooks, but I'm warning you against this because it's quite prevalent, that the amount of available work for a change is a decrease in the Helmholtz free energy. Now this is absolutely wrong. For one reason and one reason only. The free energy of the system is U minus Ts, but that T is the temperature of the system. Here the T is the temperature of the reservoir. So, we have to be very careful. This T being the temperature of the reservoir has nothing to do with the system as it's changing its state. The temperature actually would never perhaps reach T in the process. And in any case, in order that this be equal to negative of the Helmholtz free energy's change, this would have to occur at a constant temperature. Of course, if the process happened at a constant temperature, that of the reservoir, then and only then would work done be bounded above by minus delta F. Otherwise, the expression that you see on the right hand side of the available work theorem has really nothing to do other than being the same in dimension and looking superficially similar with the Helmholtz free energy's change. Now, note also that the equality will be obeyed only if the entropy change of the universe were equal to 0, and that's possible only for a reversible process. Since all real life processes are actually irreversible, you will never really attain T delta S minus delta U, but you can aspire to get close to that. Before we go on to the next application of the second law, it will be perhaps useful to recapitulate exactly what the second law is. Of course, during these lectures you have seen many variants of the second law. The one I am going to focus on right now is basically a version due to Clausius. His famous statement went as follows: the energy of the universe is a constant while its entropy keeps on increasing. The formal version of this law, stated with a bit less flair, is the following: an adiabatic system which is closed. Of course, we need to add that. So, basically an adiabatic system which is closed in the sense that it does not allow energy or number of particles to be exchanged with something else and has a fixed volume. This can only evolve towards increasing S. Now, the question that we can naturally ask is, what does this tell us about systems which are not isolated, which are in contact, say, with reservoirs? In order to see that, let's take a look at two different but important scenarios. Firstly, let's take a look at a closed system. Closed in the sense that it cannot exchange particles with its surroundings, but one which is held at constant volume and temperature. So maybe it's enclosed in rigid, immovable walls and it's in contact with a thermal reservoir at a temperature T, as you can see in the picture right now. So what you have in this case is when the system undergoes a change from the state I to the state F, of course you have a change in the internal energy given by UF minus UI and a change in the entropy given by SF minus SI, delta U and delta S respectively. Now in this case, since the volume of the system is held fixed and we are dealing with only simple systems where the only means of doing work is hydrostatic by changing volume, here there is no work which is being done on our system. So for our system, the heat that flows in, Q, has to be equal to the increase in its internal energy. Remember, this is no longer an adiabatically contained system. It's in thermal contact with a reservoir. So as the change takes place, heat will either flow in or flow out of the system. How much flows in can be easily figured out by calculating what delta U is. Now, delta U flows into the system. What flows into the reservoir is minus delta U. And as we have already seen, how do you calculate the entropy change of the reservoir? You just divide this heat flowing into the reservoir minus delta U by its temperature T. Remember, in this case, the temperature T is not only the temperature of the reservoir, it's also the temperature of the system because it's held in thermal contact with this reservoir throughout. Now, what about the entropy change of the universe? Remember, that is what is supposed to be non-negative. That's of course delta S, the entropy change of the system, minus delta U by T. And if you take the minus 1 by T out, you get delta U minus T delta S. Using the fact that T is a constant throughout, you can move it inside the delta and you can rewrite this whole thing as minus 1 by T times delta of U minus Ts. This really is the decrease in the Helmholtz free energy. So minus delta F by T is the delta S of the universe. And this has to be non-negative, either greater than or equal to 0. But note, the temperature, at least for all our classical systems, is definitely positive. So this tells us that the only way in which a system which is held at constant volume and temperature can evolve is in a direction of decreasing Helmholtz free energy. So the only evolution that will take place, if any, is a direction in which F goes down. And as a result, such a closed system, when I say such a closed system, I mean something which cannot exchange particles with the surroundings but held at a constant temperature and volume, will be in equilibrium once F reaches its minimum possible value. Because once it reaches the minimum possible value, F cannot decrease any further and therefore no further change can take place. Note that this is nothing but the second law which says that for an isolated system, and the universe of course is an isolated system, entropy can never decrease. We are just rewriting this in terms of parameter changes only of your system by taking into account the entropy change of the surroundings, using the fact that the system is held at the same temperature as the reservoir and its volume is fixed. Now, while a system at constant volume and temperature is quite a darling for physicists, because physicists usually try to explain things that are going on, if you hold volume constant, that essentially means that you are holding the boundary conditions of your system constant. So if you were to do a microscopic theory, be it classical or be it quantum mechanical, you would have the advantage of not having to worry about the boundaries moving. However, if you look at a practical scenario, you would be much better off thinking of a system at constant pressure and temperature. It's actually way easier to hold the pressure of a system fixed. All you have to do is make its wall, or at least part of its wall, movable, and expose it to a constant pressure environment like that atmosphere. And so, for practical reasons, we would want to look at equilibrium for such a system. A closed system, a system which does not exchange particles with the surroundings, but held at constant pressure and temperature, unlike the previous case where the volume was constant. Now, in this case, of course, things change slightly. Now, since the volume can change, and usually does when the process takes place, in addition to delta U, the increase in internal energy, you also have the amount of work which this system will do, plus P delta V. And these two things have to be supplied by heat flowing in from outside. So Q, the heat flowing into our system, is given by the change in U plus PV. Note that P being a constant can move into the delta, and this of course is H. So in this case, as we have already seen earlier also, the heat absorbed is given by the change in the enthalpy and not the change in the internal energy. We have already said before that the reason why chemists, who are very practical people, like the enthalpy more than internal energy is precisely this reason. Ask any chemist, they will say enthalpy is related to the heat of the reaction, how much heat a particular change of state produces. But of course, they are assuming that their change of state is happening at a constant pressure. Now, if delta H goes into the system, minus delta H goes into the reservoir, so the entropy change of the reservoir is minus delta H over T, and entropy change of the universe is when you get to add this minus delta H over T to delta S. Once again, we play the same game. We take minus 1 by T out. This becomes delta H minus T delta S. And because T is fixed throughout, you can move it in. And once again, remember, this T is the temperature of the system as well, because it's in thermal contact with the reservoir throughout. So, ultimately, in this situation, when the system can change volume but is maintained at a constant pressure, delta S of the universe is given by negative of delta G over T, and of course this has to be positive or zero in such a situation, and which tells us that for a closed system at constant pressure and temperature, the system can only evolve towards a state with a lower Gibbs free energy. So, if a particular change of state raises the Gibbs free energy, that will never happen if you are maintaining the system at a constant temperature and pressure. Of course, it can happen under other conditions, but as long as you are measuring T and P constant, the only possible evolution is towards lower G. Now, once again, it's easy to see that if such a system, a closed system held at constant P and T, will be in equilibrium when it reaches the minimum possible value of the Gibbs free energy. This is actually a very important point and will come in extremely handy when we talk about theories of chemical reactions or phase transitions. If you want to understand why there is a triple point of water and not a quadruple point where four phases coexist for pure water, or why the coexistence of water and steam occur along a curve and not along a spread out region, this is what you need to consider. We will discuss all this in a later lecture. Now, let me end this video with a puzzle. In fact, this issue used to worry me quite a lot when I first learned about these topics, like the fact that the free energy, the Helmholtz free energy of a system tends to a minimum when it's held at constant temperature and volume, and so on. Now note that according to what we have studied so far, f t, v, n, f expressed as a function of temperature, volume and number or amount of particles, has complete thermodynamic information. Then, if you have a closed system that is fixed n, and you hold it at a fixed temperature and fixed volume, how can the system even evolve? After all, what we have been talking about so far is a system that can be described completely in terms of three variables, and complete information is available for the Helmholtz free energy if those three variables happen to be temperature, volume and number of particles. What does it even mean to say the free energy reaches a minimum? After all, if T, V and N are all fixed, how does it even change from whatever value it has? Well, you should realize that the same question can also be asked equally well for G as a function of temperature, pressure and number of moles. And in fact, indeed, about U when you hold it as a function of S, V and N. Or look at it the other way around. The second law, the original version that we stated was for a system which is adiabatic, constant volume and constant number of particles, that is the whole universe, entropy tends towards a maximum. The question that one could very well ask is, if U, V and N completely describe S, which is just a restatement of S, V and N completely describing U, then how does the question of evolution even arise? What does it mean when we say that the universe which is equilibrium when entropy has reached a maximum? How can it even change, let alone get to a maximum? Now, the resolution of this puzzle should be pretty clear to you if you think about the universe example. But I will leave you to worry about it, at least until the next video, where we will answer this question in some detail and see how this actually has very important practical applications. Bye till then.